Right, get started here. So we will, as promised, have our problem session after class from 1 to 2. I'm in classes. Oh shoot! Classes at noon, right? Yeah, so why did I say that? I better check. Well, anyway, I think this one is available, but gotta jumpstart. It is Monday, so start that brain. That's what we say. Okay. So, we have for the these first lectures of the semester talked about the simplest possible kind of atom, an atom with one positive charge, one negative charge, and essentially we can solve that exactly, at least in the non-relativistic approximation. We can solve it exactly, and relativistically we can do pretty well. Of course, most atoms have more than one electron or one bound particle, and most of thinking about the problem of atomic structure and the complications and richness of atoms comes from, of course, the many-body problem associated with multi-electron atoms. And we could spend the rest of the semester talking about that. We're not going to do that. We're going to give us some of the basics. We'll discuss some of the general ideas, enough for us to get started thinking about then the atom then as a tool that we're going to use and manipulate through its interactions with electromagnetic fields. So we'll just get some of the basics. We'll spend the next essentially 2 weeks talking about atomic structure, and then we'll move on. But to make a little bit of headway on that, we want to move on from hydrogen. And so, of course, the next thing to think about is helium. Or, more generally, helium-like atoms. And what we mean by that is thinking about having a nucleus, with some atomic number and 2 electrons. So really we're talking about 2 electron atoms, helium being the neutral case of this with Z equals 2, but we can think about the problem a little bit more generically. So we have now position of electron 1, position of electron 2, and some vector between the 2 electrons. And so in just thinking about the electrostatic part of the interaction, our Hamiltonian here in the rest frame of the nucleus involves the kinetic energy of the 2 electrons, the attraction of each electron to the nucleus, and the repulsion between the 2 electrons, so called repulsion. Oops, I better remember that that's there. I'll remember now. All right. So this is the Hamiltonian, then the goal then is to solve for the eigenstates of the system, and in particular the eigenstates corresponding to the bound states corresponding to the 2 electrons bound to the nucleus. Straightforward to say it, impossible to solve exactly, unlike hydrogen. We have some complications here. Now we're talking about a many-body problem. With more than one electron. And we have to think about the problem of identical particles. So the 3-body problem, of course, we know is not even solvable classically. We cannot solve for the exact dynamics of 3 bodies interacting, say, through a gravitational potential. It's not an integrable problem. Generally, there's chaos associated with those classical dynamics. So it's no surprise that there's not an exact quantum solution to this either. So many-body physics really is much of the richness in physics and it was really developed and started in thinking about multi-electron atoms. So many of the techniques that are at the base of thinking about solid state and condensed matter were born in thinking about how one was able to model and treat the energy levels associated with atoms. All right. Now, beyond this many-body aspect to it, which, as I said, has some classical issues, even, I mean, it's an issue even in classical physics. There's the specialness associated with the fact that if we're thinking about multi-electron atoms with more than one electron, we have to deal with the issue of identical particles. So to remind you, of course, what we know is we have electrons or fermions, so we have to think about we have fermions, the electrons. And so we have the requirement that if I exchange any two, well, in this case, let's just say we have 2 electrons. So we have electron 1 and electron 2, that whatever the state of the system, the state must pick up a phase of -1 if we exchange so this is the joint state of the 2 electrons. And this is the exchange operator. Now, what is the exchange operator? Of course, what we mean when we say we apply some exchange of the 2 particles, what we mean is we exchange all the labels associated with those 2 particles. So in the context of our 2 electrons here, we're talking about exchanging both their quantum numbers associated with the orbital motion of, or the motional degrees of freedom, as well as the spin degrees of freedom. And of course, what that means is that spin plays a very profound role in the structure of multi-electron atoms, much more profound than it did in hydrogen. In hydrogen, it played a role because of the effect of magnetic effects, which we can think about as relativistic corrections. So there was a magnetic effect having to do with the spin, and that led to the fine structure. There is also, as we will discuss, fine structure in multi-electron atoms, and that gives us corrections to the base energies that arise from this electrostatic potential. But there is a much more profound effect having to do with the identical particle statistics, because the spin state of the electrons profoundly restricts the possible motional states of the electrons. And the motion of the electrons determines where they are and how much interaction there is between the electrons. So there is a connection between the electrostatic forces that the electrons feel and their spin. It's not a spin force in a sense of the spin has magnetic moment, and that gives the usual kinds of things we think about spin. It's the connection between spin and statistics that affects electrostatics. The forces here are all electrostatic forces, but the spin has a profound effect on those electrostatic forces, as we will remind ourselves. Okay. What can we say about then this connection between spin and statistics? Well, we can think about possible states, just to remind us about allowed states for Fermi statistics. So let us imagine that let's imagine phi A and phi B to be two orbitals. That is to say, spatial wave functions of an electron. So we want to think about now, what are the possible states allowed in which one of the electrons is in orbital phi A and another of the electrons is in phi B. Maybe phi A and phi B are the same orbital, or maybe they're different orthogonal orbitals. Let's just leave that general for now. To fully specify the state, we need also to think about the spin. So of course, in addition, electron can be spin up or down, or any linear combination of spin up and spin down. But we can think about basis vectors for the two electron states, where one of the electrons is in this orbital, the other one's in this orbital, and the electron is either in spin up and spin or spin down. That will determine a basis restricted to this spatial orbital space, right? So let's see what notation I want to use. Just okay. So let me let chi A and chi B be this spin state. I'm not telling you where the chi is up or down. It's just one of these electrons is in state chi A and the other is in state chi B. And now, what do we have? Well, let's write down the joint state of the two electrons. I can have electron 1 in orbital phi A, and then electron 1 is in spin state chi A, tensored into the electron in this state. But that does not respect the Fermi statistic. So I have to anti-symmetrize. Which means I have to put electron 1 into state B and electron 2 into state A, because it has to be antisymmetric with respect to exchange of the degrees of freedom. So here, 1 and 2 label the rich electron I'm talking about, and A and B represent particular states in which those electrons find themselves. Okay? So, what can we say about this? Well, let's take the case that the two spin states were equal. I'm not telling for they're up or down, but they're both the same. They're both in the same spin state. Well, in that case, of course, what we have is this is the only possible state of the two electron system. So in this case, what we have is a situation where both electrons are either both up or both down, and the spatial wave function is antisymmetric. Antisymmetric here with respect to exchange, not parity. This has nothing to do with that kind of antisymmetry where we're flipping the position of the electron relative to the origin. We're flipping the labels of those electrons. Of course, then we have symmetric spin. Doesn't matter if I exchange 1 and 2, this is the same state. On the other hand, let's imagine another case in which the two spins are in opposite states. One is up and the other is down. So So what I mean by this is either I have one chi A is up and chi B is down, or vice versa. In that case, the joint state of the system is decomposed into the following. So I can have the same kind of antisymmetric spatial wave function, which is now paired this way. Let's see this here, because we're going to use it in a moment. So what do we have in this case? In this case, we have many more possibilities. Either we have the antisymmetric spatial wave function, which is paired with a symmetric spin pairing, or we have a symmetric pairing of the spatial orbitals correlated with the antisymmetric pairing. I guess I'll come back to this. Right? So we can have the following basis states. So the following basis states are allowed. Either we have the states that we just discussed on the right-hand side of the board, where we have an antisymmetric pairing of the spin, I'm sorry, of the space. Let me do the symmetric one first, because that's actually symmetric with antisymmetric. Or we have a symmetric pairing of the spin with an antisymmetric pairing of the space. Let me write it down. And the possible states here are that either both in the same state, which is they're both up, or they're both down, or they're symmetrically up and down. Let's take a look at this again. Let's just remind ourselves. What do we see here? Because of the identical particle statistics, as you remember, we have this pairing which correlates how the spatial wave function, what its symmetry is, with the spin state. And what we notice here, and what we remember, is that the symmetric and antisymmetric spin states, for the case of two electrons, for the case of two spin 1/2 particles, are also the states of total angular momentum of the two spins. So we see here this particular single spin state is what we call the spin singlet. It's the state with total spin 0. And therefore the total m to s is 0. And that state is also an eigenstate of exchange of the two spins with eigenvalue -1. So if I have two electrons and the spin and the space separate, then the spin state of the two electrons must be a singlet if I have the spatial wave function symmetric. On the other hand, the other possible states are the states where the spatial wave functions are antisymmetric, meaning that if I exchange which orbital the two electrons are in, I pick up a minus sign. That must be associated with a state in which the spin is symmetric under exchange. And this state, these states are also eigenstates of the total spin angular momentum, with total spin 1, and there are 3 possible total m sub s values. And of course we call this the spin triplet. So if I have 2 electrons and I need to worry about the identical particle statistics, then I can have a pairing in which I have the spin singlet correlated with the symmetric wave function, or the spin triplet associated with the antisymmetric. Okay. This has only to do with identical particle statistics. It has nothing to do with angular momentum or magnetic fields. It only has to do with angular momentum to the degree that spin and statistics are connected to one another. All right. So this gives us this restriction on the possible states. And now we can return to try to think about how we're going to solve for the energy levels of helium. Once again, let's write down our Hamiltonian. Now I'm going to write it down in a particular way. What can we notice about this Hamiltonian? Well, each one of these Hamiltonians, is it Hamiltonia? Don't know. These Hamiltonians are the Hamiltonians for each electron independently. And then we have a Hamiltonian having to do with the interaction between the two electrons. So given that, we could think about a very kind of coarse approximation where, for the moment, let's just ignore the interaction between the electrons. That's probably a terrible approximation, and it certainly will be for helium, as we'll get to in a moment. It might be okay for a very heavy nucleus with a big, big Z, where the electron is very, very close to the nucleus and they're very far from one another, so that the repulsive energy is negligible. But we can just sort of at least start to get started in thinking about the problem a little bit. So if I take H0 to be just the sum of the two independent electrons, well then we know what the energy levels are under, this is what we would call the independent electron model. Probably terrible. We'll see how terrible it is in a moment. What are the bound states of this? Well, they are the energies, the bound state energies of this Hamiltonian are just the sum of the bound state energies of these, because this is a separable Hamiltonian. And each one of these is, of course, just a hydrogenic Hamiltonian, right? That's to say, it involves one electron in the Coulomb potential of this nucleus. So what is the energy for each of these? The energy, the hydrogenic energies, which are, these depend on a principal quantum number. So there's a principal quantum number for electron 1 and a principal quantum number for electron 2. Now, I don't know which one is electron 1 and electron 2 because we're going to have to anti-symmetrize, but one of them has an energy z squared, no, that's not me, z squared over 2 and I'll call it n1 squared, and then there's so there are two principal quantum numbers, one associated with electron 1 and one associated with electron 2. And these were, right, this in atomic units, these were the hydrogenic energies, right? So this is the zeroth order approximation. Of course, we think about, in this case, the orbitals. We would generally write this as a configuration with an orbital n1, L1, and another orbital n2, L2. So one of the electrons is in this orbital, the hydrogenic orbital associated with a certain principal quantum number. Of course, there's also an m sub L value, but we typically don't write that down in this case. And then n and L associated with the other electron. So what does this give us for the ground state? Well, first of all, the ground state in the zeroth order what we would say is that the ground state configuration would involve both electrons in the ground state of the hydrogenic orbitals, right? So the ground state configuration we would typically write as 1s squared, meaning we have both electrons in the 1s orbital, 1s hydrogenic orbital. what is the possible spin states of the electrons in this case? Well, we have both electrons in the same spatial orbital, right? So the Pauli exclusion principle tells us that we can't have them also both in the same spin state. That's to say, if phi A equals phi B, this is not allowed. The only thing that's allowed is the symmetric case, when phi equals phi B, which means that we have to have the spin singlet. Spins paired as singlet. All right. So, in this case, the zeroth order energy would be -4 atomic units. In both cases, n equals 1. In this case, if for helium, and actually let's write it down. It's equal to -v squared, which is -4 atomic units for z equals 2 helium. Okay, and this is about 108. The binding of the two electrons relative to both electrons being free or unbound is binding of 108 electrons. The actual binding energy as for both electrons being is, what is it, 70 something. Sorry, got all these different notes here. Fine. There it is, yeah. So the ground state is, so this is a pretty bad approximation, as we kind of expected it to be.
Now, when you write 79, is that like experimentally measured or calculated in a more sophisticated way?
No, measured, yeah.
Is this to knock out one electron or both?
This is for both. So that's what I was just about to discuss. So let's discuss that. So the zero of energy of this Hamiltonian is where both electrons are at infinity relative to one another. Okay? Because the way we wrote down this energy here, we had both the binding energy of both electrons. So each one of these goes to 0 when both electrons are at infinity relative to the nucleus. So let's sketch that. So the 0, for the moment, although we'll change our picture in a moment, the 0 of energy here is the energy where I have both electrons knocked out. So I have a pure alpha particle plus 2 electrons at 0 energy. Okay? Asymptotically far away. The ground state configuration, which, so this is the ground state, which we typically write as 1s squared, even though these are not, we'll come to what that means in a moment, these are not necessarily hydrogenic orbitals anymore, is bound as measured by about -79 eV. Now we can ask the question about what is the energy, as Boyan was asking, associated with just ionizing one of the electrons and leaving the other electrons still bound so that we have a +1 charge, 1 electron charge helium ion. Well, that's a problem we can solve, because that's a problem associated with one of these orbitals at infinity, in which case the, that's to say one of the electrons at infinity, there is no electron repulsion that we care about, and that's just the energy associated with one electron bound in the helium nucleus, the alpha particle nucleus. So what is the binding energy associated with that? Well, that energy is equal to, it depends, I should really say, let's put that one of the electrons is in the ground state, and the other electron is infinitely far away. That's to say, it's in the ground state of the hydrogenic orbital associated with z equals 2. So that is the case where n1 is equal to 1 and n2 is equal to infinity. Or vice versa. It's the same thing in the picture, right? So what is that energy? That's equal to z squared over 2, which is, for the case of helium, 2. So that's twice the Hartree, and the Hartree is 27.2, so that's minus 54.4. So the binding energy, what we might call the ionization level, is about 26.4, something, I forgot what it is, 24. To subtract those, it's hard for me to do that in my head, something like that. ED is the ionization level.
So this is the potential energy that we look at now.
No, this is the combination of kinetic and potential. Remember that these energy eigenvalues were the eigenstates of both potential and kinetic. So it's both, it's the total energy. Now, of course, there is a whole continuum of states here associated with, if I had, the case of, if I had a singly ionized helium atom in its ground state and then an incoming electron. If I wanted to look at some kind of scattering process associated with that, I would say there is a channel, a scattering channel associated with the zero energy impact of that electron, which would be right here, but then there's a continuum of possible energies associated with that, the motion of that free electron impacting on that ion. Of course, there's other states here. There's states like the helium, the hydrogenic or 2s plus an electron, right? Which is the exciting that helium nucleus, and then there's all the free electron states up there. Now, what about the case where, from some approximation here, if we thought about it, and we look at the states where both of the electrons are excited, that energy is always going to be higher than the energy where one of these guys is at infinity. Right? If either n1 or n2 is finite, that energy is going to be higher than where one of these guys goes infinity. So the case, even if I look, let's look at the case where I have the situation where both electrons have n greater than 1. The situation where both electrons have a principal quantum number n greater than 1, that energy there will always be bigger than the case where one of the electrons is at infinity, that is to say, one of the principal quantum numbers is at infinity, and the other is in whatever state it wants, right? So that means that there are states up here which are the states with doubly excited electrons, but they're above the ionization level. They're above the level in which one of the electrons is bound and the other is at infinity. So what these electrons are called auto-ionizing states. That's to say, I mean, of course it takes some time for the electrons to move. If somehow I were able, in some sort of short pulse situation, excite the two electrons, all of a sudden they find themselves in a potential that's not quite right, and the atom would disintegrate, and the electrons would fly apart. The bound states, the only bound states of helium, are the ones where one of the electrons is essentially in the ground state and the other is excited. Those states are below this ionization level. So there is a spectrum here. I'm going to kind of divide it up, as we'll see in a moment. It has to do with the singlets and the triplets. Which is the discrete part of the spectrum. These are the excited states of my helium atom, paired in singlet and triplet-like ways. There is the ionization level, which corresponds to one of the electrons unbound and the other electron still bound. And then we have up here a whole more complicated set of states where either one electron is still bound and the other is free, or they're both quasi-bound, but not in a stable eigenstate, coupled to the continuum, auto-ionizing. And then way up here is where both electrons are completely free and free to move about the room. Okay? Okay, so, well, our very coarse approximation didn't do so great, but we can at least do perturbation theory. At the least, we can say this is a perturbation and calculate what the shift is in the ground state due to the repulsion of the two electrons from one another. So, perturbation for the ground state. So the shift in the energy to first order is equal to the expectation value in atomic units. I'll just set the charge of the repulsion. Okay? So this is just an integral that you have to do. And the way that you would typically do these kinds of integrals is to use the addition theorem of angular momentum to express the distance between the two electrons in terms of a product, a sum of product of the coordinate orbitals of particle 1 and 2. So just to remind you, this is the kind of thing that you may have seen, for example, in your math methods or in studying electrodynamics, because this kind of potential shows up. We can re-express this in terms of the Legendres or ultimately the spherical harmonics. So let me write down the formula and remind you of what it means. So this is what's called the addition theorem. And it says if I re-express coordinates R1 and R2 in spherical coordinates R theta phi, then I can re-express this complicated thing, which is going to involve all kinds of products of the thetas and the phis and so forth, in terms of a sum of products, where the R less than and the R greater than are means, whichever one is smaller. So if the magnitude of R1 is smaller than the magnitude of R2, then this is R1 over R2. If the magnitude of R2 is smaller than the magnitude of R1, then this is R2 over R1. So the less than or greater than means whichever one is smaller goes on the top. Okay? It's a formula you've seen before? Yeah, good. Anyway, so once we do that, then we can plug in our psi so we have integral over 1 and 2, and then we have so these are the orbitals in terms of reduced radial wave functions and spherical harmonics. Of course, these are just constants, 1 over 4 pi in this case. And we plug in this and we pick off all those terms and we do the integral. And we get 5/8 thing. Z squared? Yeah. No, that's no. Yeah, I guess that's right. No, it can't be right. It's Z squared. It's wrong in the notes. Okay. So we put that together, and we get come back over here to say that to first order. Is minus z squared plus 5/8 z squared which is minus 3/8 z squared, which is equal to, what the heck is that equal to? I don't have that written down here. So it's not bad. It's not quite there, but it's not bad. Oh, that's not right. Sorry, I knew that was too good to be true. Pardon me. That's the actual level here. What you get out of here, I knew that was too close, is 74.8 per helium. Can't be that good, because we just saw that the 0th order was so far off. This was much bigger than a standard perturbation. We're going to have to come back to that. Our 0th order approximation wasn't really a good approximation to begin with, so perturbation theory can't converge. And this is off by a pretty big fraction of this binding energy, right? So it's not quite up to snuff here. This 4 EVs off. It's a pretty big fraction of that binding energy. So we'll come back to that in a moment. Let's think a little bit about the excited states. These states that we said are still bound, where starting from a different configuration. Here we started with the configuration where we started with hydrogenic orbitals, both hydrogenic orbitals being the 1s orbital. Now we're going to think about the excited states in which one of the electrons is in a 1s orbital and the other electron is in an excited orbital. So let's start with our 0th order configuration. In which one of the electrons is put in the orbital 1s and the other is in another orbital not equal to 1s. We know, of course, what we just discussed is that there is a singlet-triplet pairing here. If I have a symmetric pairing of the orbitals, then this is with the singlet. And if I have the antisymmetric pairing, then this must be paired with one of the 3 triplet states. So, what do we have here? Well, the 0th order energy, according to this, assuming the non-interacting particle model, assuming no repulsion between the atoms, where one of the atoms is in the 1s and the other is in an excited state with n greater than 1, is equal to minus e squared over 2, 1 plus 1 over n squared. And so now we need to look at that same integral that we looked at in terms of the repulsion, doing the perturbation theory with this as our zeroth order state. So the perturbation let me write it generically well. Expressed in the coordinate representation is the integral over its two coordinates. And then I have okay, so what I have written down here is this is just the probability density for the two electrons as a function of their two positions, and this is the repulsive potential energy associated with that. Where this wave function is the square of either this wave function or that wave function, depending upon whether I'm in as paired as a spin singlet or a spin triplet. So let's remind ourselves about something, the important aspect of identical particles which makes this different from a classical electrostatics problem. So let me do a little aside here. So let me consider a joint wave function as a function, the spatial wave function of the two coordinates, which is either symmetric or an antisymmetric so for example here, phi A is the 1s orbital, and phi B is an excited orbital. And we call this plus or minus. Let's look at the probability density associated with this. What do I get? I'm going to get a half plus and then the cross terms. So, what can we say about this? Let's consider operator which is symmetric under this change. It doesn't distinguish between particle 1 and particle 2. Okay, so I'm going to look at the expectation value. Like, for example, the magnitude of 1 over R1 minus R2. That doesn't depend on which particle is 1 or 2. So this is symmetric with respect to 1 goes to 2. I'm going to have an integral just like the one we wrote down. So these two terms will be the same, right? Because the only thing that distinguishes these two terms is switching R1 with R2. But they'll give the same integral. Is that clear? So this is equal to the integral over the two coordinates plus or minus the integral over the coordinates with this term. I guess it should be a star here on this guy. Yeah, actually, there's really two terms here, excuse me. There's two terms there, plus conjugate. Sorry about that. In this case, I just, they're real, so it doesn't matter, but more generally, we do have to worry about that. All right, let's take a look at this and analyze it and understand what it means. This term is what we might have thought if we just thought about this in a kind of quasi-classical way, in which there is an electron cloud associated with orbital phi A, and therefore there's a charge density associated with that, related to the square of that probability density. And there's some electron cloud associated with orbital B, and this is the probability or charge density associated with that. And we would say we would just integrate over those charge densities times whatever the interaction energy is between the two particles. This is what's called the direct term in the interaction. But there is another term, which was the interference term from the two different, the cross term, which interfered the two. I mean, we had the fact that we have this cross term has to do with the interference between these two amplitudes that came from the identical particles. And that interference depends on not knowing whether particle 1 or particle 2 was in the orbital phi A or phi B. Let me write this in a slightly different way. Let me just... Okay, that's just this conjugated. what do I see here? What I see is that depending upon the overlap of these two orbitals, this term can either be big or small. If the two orbitals have no overlap at all, so if I have one electron in this wave packet and one electron in this wave packet, and I don't know which one it is, well then the product of these is 0. However, if phi A and phi B start to overlap, then I can't tell whether the particle was in this orbital or that orbital. And this is what's known as the exchange term, because it has to do with the exchange of particles. If I didn't have the exchange, I would still have this term. This is what I would imagine if I ignored identical particles. But this term becomes important when the orbitals start to overlap. So this is why, of course, we don't have to anti-symmetrize over all electrons in the universe, even though in principle we should, because the contribution of all the other electrons, which have absolutely negligible probability to be where I am, don't contribute in any way to the exchange terms. The only time we need to worry about identical particle statistics is if the two particles can actually be in the same place at the same time. And obviously in an atom, we gotta worry about that. So, with that said, we can calculate what this integral is. And what we're going to get is a term like the first term, where phi A and phi B are the, say, 1s and NL orbitals.
It's supposed to be R2.
It is supposed to be R2. Thank you. And we have the exchange term. And this is generic, or is typically written as, for lack of better letters, but who made it, is called J plus or minus K. Where this is the direct term, and this is the exchange term. That is to say, if I plug in here the square of the 1s orbital and the square of the np orbital and integrated that, I get some positive number, right? Because this is a positive function, and we're integrating it over positive probability distributions. And that gives us this thing, J. And then we get the interference terms, which had to do with the exchange. And that is where one of those orbitals is the 1s and the other is 1p, and we have the exchange term, and that is k. And the values of those will depend on which orbital I'm talking about. So of course, the plus sign, as we said, is associated with the singlet. And the minus sign is associated with the triplet. Why is that? Why does physically it make sense that the singlet should have higher energy than the triplet? Remember where this excess energy is coming from. This excess energy is coming from the repulsive energy associated with the two electrons. So why should the singlet be at higher energy than the triplet?
Because
because singlets are close to each other.
That's right. The exchange term enhances the probability for two electrons to be in the same place. There's excess probability. Singlets have excess probability to be on top of one another, depending on the overlap of these orbitals. Whereas triplets, because of the Pauli exclusion principle, can't be in the same place because they have symmetric or the same spin state. It's not really just, we usually talk about in high school chemistry this, they're in the same spin state, but just that they have to be in a symmetric spin state. The same is an example of symmetric, but it's not the only example. I could have this and this, but symmetric with respect to exchange or something like that. So there is excess repulsive energy associated with the singlet and less repulsive energy associated with the triplet. So we can think about this from a perturbation point of view, is that I had the 0th order state. I have some repulsion ignoring the identical particle statistics, but then I get a splitting here where the singlet is higher energy than the triplet. So, just to conclude this lecture, and then we'll finish it up next time, the energy spectrum of the bound states of helium, where both electrons are bound, looks like the following. I need to combine these two notes because I'm going to write down some notation, then I'll define it in a moment. So now I'm going to call 0 energy the energy associated with 1 electron unbound. Okay? So the binding energy, the ground state, was 24.6 eV. So here's minus 25 eV. Here's minus 5. This is in electron volts. So here's the ground state. And it has this notation that we'll discuss in a moment. Configuration is 1s squared. The term is singlet s. Why is the ground state singlet? Because both electrons are in the same orbital, so we have to have the electrons paired antisymmetrically in a singlet. Then we have here the situation with, gosh, I don't remember. I'll have to look at these numbers. I think I'll write this down here. 1s, 2s, singlet s. And then we have the triplet at a lower energy. We'll be done in a moment. Then up here I have the 1s, 2p, singlet p. S, 2p, triplet p. So what does this notation mean? We have here different configuration, I mean the same configuration with singlet and triplet. The triplet is lower energy than the singlet. The same configuration singlet versus triplet. What does this letter mean? So spectroscopic notation, which we will expound upon next time, is written the following way. L 2s plus 1j. This is what's called a term. L here represents the total orbital angular momentum. What goes up here is the multiplicity. And this is the total J when we include fine structure. Both spin and orbit. So if I have one of the electrons in an s orbital, then the total angular momentum is just the angular momentum orbital is the angular momentum of the other orbital. In this case, both of them are in s, so this is the total angular momentum is s. Remember, s means two different things. S means L equals 0, and in this case, s means spin. Didn't make that stuff up. So we'll talk more about this, but one will see if you look at, spectrum, this is a singlet S, whatever, but then there's a configuration associated. Okay. We'll pick this up next time. Let me check that the room is available. I believe it is, and we'll take a 10-minute break, and we'll meet up for a problem session in 11:31. Multi-electron atoms with more than one electron, we have to deal with the issue of identical particles. So to remind you, of course, what we know is we have electrons or fermions, so we have to think about Fermi. We have fermions, the electrons. And so we have the requirement that if I exchange any two, well, in this case, let's just say we have two electrons. So we have electron 1 and electron 2, that whatever the state of the system, the state must pick up a phase of -1 if we exchange so this is the joint state of the two electrons. And this is the exchange operator. Now, what is the exchange operator? Of course, what we mean when we say we apply some exchange of the two particles, what we mean is we exchange all the labels associated with those two particles. So in the context of our two electrons here, we're talking about exchanging both their quantum numbers associated with the orbital motion or the motional degrees of freedom, as well as the spin degrees of freedom. And of course, what that means is that spin plays a very profound role in the structure of multi-electron atoms, much more profound than it. Right. Get started here. So we will, as promised, have our problem session after class from 1 to 2. I'm in classes. Oh shoot! Classes at noon, right? Yeah, so why did I say that? I better check. Well, anyway, I think this one is available, but gotta jumpstart. It is Monday, so start that training. That's what we say. Okay. So, we have for the these first lectures of the semester talked about the simplest possible kind of atom, an atom with one positive charge, one negative charge, and essentially we can solve that exactly, at least in the non-relativistic approximation. We can solve it exactly, and relativistically we can do pretty well. Of course, most atoms have more than one electron or one bound particle, and most of thinking about the problem of atomic structure and the complications and richness of atoms comes from, of course, the many-body problem associated with multi-electron atoms. And we could spend the rest of the semester talking about that. We're not going to do that. We're going to give us some of the basics. We'll discuss some of the general ideas, enough for us to get started thinking about then the atom then as a tool that we're going to use and manipulate through its interactions with electromagnetic fields. So we'll just get some of the basics. We'll spend the next essentially 2 weeks talking about atomic structure, and then we'll move on. But to make a little bit of headway on that, we want to move on from hydrogen. And so, of course, in hydrogen. And hydrogen played a role because of the effect of magnetic effects, which we can think about as relativistic corrections. So there was a magnetic effect having to do with the spin, and that led to the fine structure. There is also, as we will discuss, fine structure in multi-electron atoms, and that gives us corrections to the base energies that arise from this electrostatic potential. But there is a much more profound effect having to do with the identical particle statistics, because the spin state of the electrons profoundly restricts the possible motional states of the electrons. And the motion of the electrons determines where they are and how much interaction there is between the electrons. So there is a connection between the electrostatic forces that the electrons feel and their spin. It's not a spin force in a sense of the spin has magnetic moment, and that gives the usual kinds of things we think about spin. It's the connection between spin and statistics that affects electrostatics. The forces here are all electrostatic forces. But the spin has a profound effect on those electrostatic forces, as we will remind ourselves. Okay. What can we say about then this connection between spin and statistics? Well, we can think about possible states, just to remind us about allowed states for Fermi statistics. So let us imagine that the 2 electrons bound to the nucleus. Straightforward to say it, impossible to solve exactly. Unlike hydrogen. We have some complications here. Now, we're talking about a many-body problem. With more than one electron. And we have to think about the problem of identical particles. So the three-body problem, of course, we know is not even solvable classically. We cannot solve for the exact dynamics of three bodies interacting, say, through a gravitational potential. It's not an integrable problem. Generally, there's chaos associated with those classical dynamics. So it's no surprise that there's not an exact quantum solution to this either. So many-body physics really is much of the richness in physics and it was really developed and started in thinking about multi-electron atoms. So many of the techniques that are at the base of thinking about solid state and condensed matter were born in thinking about how one was able to model and treat the energy levels associated with atoms. All right. Now, beyond this many-body aspect to it, which, as I said, has some classical issues, even, I mean, it's an issue even in classical physics. There's the specialness associated with the fact that if we're thinking about, the next thing to think about is helium. Or, more generally, helium-like atoms. And what we mean by that is thinking about having a nucleus, with some atomic number and two electrons. So really we're talking about two electron atoms, helium being the neutral case of this with Z equals 2, but we can think about the problem a little bit more generically. So we have now position of electron 1, position of electron 2, and some vector between the two electrons. And so in just thinking about the electrostatic part of the interaction, our Hamiltonian here in the rest frame of the nucleus involves the kinetic energy of the two electrons, the attraction of each electron to the nucleus, and the repulsion between the two electrons, the core repulsion. Oops, I better remember that that's there. I'll remember now. All right. So this is the Hamiltonian, and the goal then is to solve for the eigenstates of the system, and in particular the eigenstates corresponding to the bound states corresponding to the